So, like I said, we're going to finish these section 1.4 notes. So these will be section 1.4b on the YouTube. And they're pretty much separate from what we were doing yesterday. Yesterday we were doing arithmetic with functions, right? Add, subtract, multiply, divide functions, find their domains. And then we also did composing of functions, so plugging one function into another, finding domains, and decomposition of functions,
Mr.
taking it
M,
apart.
I can't hear you.
Today, I forgot to share the screen. Today, we are going to talk about relations, mathematical relations, I should say, before I get fired. No chuckles at all. Okay. All right. Well, it says determine which of these ordered pairs, and I give you 3 coordinates, are on this relation: x squared y plus y squared equals 5. Now that is not that I can't call it a function because I don't actually know yet. Look, it says, is it a function? I don't know. So it's just some kind of relation in terms of x's and y's. First, we're going to figure out which of these 3 are points that exist on its graph. And then we'll talk about whether or not it's a function without graphing it. Well, we legitimately are just going to plug in those x's and those y's and see if we get a true math statement. So we're going to plug in 2 comma negative 5 like this. So we get 2.
Mr. M, sorry to interrupt again, but we still can't hear you, but we can see what's on the board.
Well, this video's wrecked. So all that talking I did, they're just now going to tell me? Okay. And didn't one of you tell me that you could hear me? I asked if they could hear me, and they said yes. All right. Dog nabbit.
I think the problem is you're muted on Zoom.
Why am I muted? Oh, yes, I was muted. That's right. How about that? Thank God Daniel's here. All right. Appreciate you, Daniel. I wish I knew how to edit videos so I could cut all this out. Oh, well. So, the heck was I doing? Oh, that's right, educating. Okay, what are we doing? We are plugging in x's and y's to see if these coordinates actually exist on this wacky-looking equation we have. So we have x is 2 and y is negative 5. So 2 squared and our y value, negative 5. That's a horrible 5. And then plus our y value squared, and we're legitimately curious, does this equal 5? And if it does, yay, it's on the relation. What do we got? We have 4 times negative 5, showing a lot of work, and negative 5 times negative 5 being 25. Still curious, does this equal 5? Well, 4 times negative 5 is negative 20. So yeah, it does equal 5. So the coordinate 2 comma negative 5 is part of that relation. So we're just verifying which ones work and which ones do not. Let me scroll down a little bit. And now let's plug in 1 comma 3, the exact same way. By the way, equal sign with a question mark over it, I don't think that's real math. I just did that because it's what I was thinking. I wonder if this is equal. X is 1, y is 3, plus our y value squared. Curious to know if that equals 5. Well, 1 squared times 3, I think I could show less work on this one. 1 squared times 3 is just 3, and 3 squared is 9. And that equals not 5. So no, the coordinate 1 comma 3 is not on this relation. And then lastly, let's plug in 2 comma 1 and see what happens. Two squared times 1, well, that's just 4. And 4 plus 1, yeah, that equals 5. So that coordinate is also on the relation. So we know that 2 comma negative 5 is on my graph, and we know that 2 comma 1 is on my graph. So is this a function? No. It's not a function because the definition of a function is for every x, there is a unique y. What that means is if I have one x value that points at 2 different y values, I have 2 points that exist within a vertical line, so it would fail the vertical line test. So because x equals 2 points at 2 different y's, no, this is not a function. It is a relation, it is graphable, Desmos will do it for us, but it would not be a function. There you go. So I told you Desmos would graph it. I don't think a graphing calculator will, though. No, don't try it. And so what if you did want to graph it on your graphing calculator? And the reason why I said I don't think a graphing calculator can do it is because, well, if you hit the y equals button, you're implying you can isolate y. Sometimes you can, sometimes you can't. If you have the ability of getting y by itself and solving for y, then the graphing calculator could graph it. But what would normally happen is you would end up with more than one equation for y. We call these implicitly defined functions. Take this circle, for example. X squared plus y squared equals 4. Centered at the origin, radius of 2. 2 squared is 4. Well, it's not a function. It's a circle, right? Vertical line test fails all over the place. But you do have the ability to solve for y. You can isolate y. So subtract x squared from both sides. You get y squared equals 4 minus x squared. And then just cancel the square with the square root. And we talked about this yesterday, but I'm going to reiterate it. When you cancel an even power with an even root, it creates a plus or minus. Now that only happens when you cancel an even power with an even root. Yesterday, I canceled an odd power with an odd root. It did not create a plus or minus. And the reason why is because when you square a positive number, you get a positive number. And if you square a negative number, you still get a positive number. So we have to say plus or minus because squaring things hides negative values from us. The plus or minus implies that there are 2 different functions. One of them is y equals the positive square root of 4 minus x squared, and down here is its graph. It's the top half of that circle. And then the other side, y equals negative square root of 4 minus x squared, is the bottom half of the circle. Question or stretch? Oh, okay. Someone first period asked the same question. Why don't we simplify? You mean take the square root of 4 and the square root of x squared. The reason why is because you can't. That minus sign is stopping you. Now, if it had said 4x squared, you could take the square root. But the plus or minus stops you from doing it. It's like, for example, let me just throw an example up real quick, and instead of using variables, let's use 2 perfect squares. Ready? Square root of 9 minus 1. It's not 3 minus 1, because 3 minus 1 is 2, right? The square root of 3 is, or the square root of 9 is 3, and the square root of 1 is 1. So you try to, quote unquote, simplify this to 3 minus 1, but you can't, because 9 minus 1 is 8, and the square root of 8 is not 2. So there's actually no way to simplify. You could factor 4 minus x squared as 2 plus x times 2 minus x, but you'd never be able to take the square root until you know what x equals. If it said square root of 4x squared, oh yeah, you could do that. So that y equals negative square root 4 minus x squared, that's the bottom half of the circle. And that's what you're seeing right there. Your calculator will do that. It wants you to say what y equals. That's why the button has y equals on it. It can only graph functions in a certain mode. Can we get it to graph non-functions? Yes, we can. And I'll show you how to do it at a later point in time. Next week, I think. So this is called, it says, since all of the ordered pairs in either of these functions satisfies that equation of the circle, we say that the relation given by the equation defines the 2 functions implicitly. Now, the neat thing about defining functions implicitly is we kind of do it right now, right at the beginning of the year, right? The very last concept I'm going to teach you this year has to do with this exact thing. Only it'll be in calculus. So it's kind of cool. Start the year with this idea, end the year with this idea. Put a pretty little bow on it. Basically, if you can get y by itself, you can define a relation implicitly. Cool? Just use some algebra to solve for y. For example, we've been asked to describe the graph of this relation. It's probably not a function, and the dead giveaway for that is we see x's and y's being squared. When you see that kind of thing happen, generally you break the rules of functions. But how do we get y by itself is the question. How can we isolate it? If we bring x squared to the other side, we would hope that there'd be a way of getting that y all by itself. But the problem is, if you move this x squared to the other side, the only thing you could do on the left is factor out a y. But you'll still have a set of parentheses that has a y in it with an x. So that doesn't work. Now, the only way to get y by itself on this one is to realize really fast that it looks kind of like this. And then realize that it's a perfect square trinomial. This statement factors. You see, this perfect square trinomial would have factored to x plus 1 squared. Well, the one that's in the question, x squared plus 2xy plus y squared, replaced my 1 with an with a y squared. So it actually factors to x plus y squared equals 1. And our job now is to just get y by itself. Is that something that a student would have been on the lookout for? Probably not, until now. So that's a pretty powerful idea, factoring something using maybe completing the square is an option. Maybe it's a quadratic, quote unquote, but it's got x's and y's in it. This is some form of quadratic. I mean, there's the proof. It factored into something squared. Be on the lookout for that kind of thing. Perfect square trinomials, in case you don't know how to recognize them. A perfect square trinomial has a perfect square in the front. It's got a perfect square in the back. And the middle term will be double the product of the square roots. Square root of the front is x, square root of the back is y, and in the middle you see 2 times x times y. So that's how you see them. Square in the front, square in the back, double the product of the roots in the middle. So at this point, we just need to get y by itself. And we can do that with just regular old PEMDAS in reverse order. Just do some sad MEP. Take the square root of both sides to get rid of that exponent. Canceling an even power with an even root creates a plus or minus on the right side. And a plus or minus, or the square root of 1 is 1. Bloop, like that. X plus y. And you get y by itself by subtracting x from both sides. Y equals negative x, and I did put it in the front for a reason, plus or minus 1. How in the world would we know what that graph looks like? Strange, right? He grabbed the graphing calculator. He can't do it. He doesn't believe me. It can't graph functions. You can't find the plus or minus key on that calculator. It doesn't exist. But what you could do is you could separate it into 2 different functions. Y equals positive x minus 1. Excuse me, negative x minus 1. And y equals negative x plus 1. So instead of saying plus or minus, just list them both. This relation ends up being 2 straight lines. More specifically, what kind of lines? Parallel lines. They have the same slope. So that function, that relation, bad word. That relation, x squared plus 2xy plus y squared equals 1, is the graph of 2 parallel lines. Neat. And like I said, Desmos can graph this. You can type x's and y's in Desmos, and it'll graph it for you. So if you're checking your answers at home and you didn't want to use the websites that tell you where all the answers are, you could use Desmos. And that finishes the notes. This is what we didn't get to yesterday. But I imagine for those of you that start to try the homework, might have struggled a little bit. Not to mention, you didn't get to see some of the really interesting questions. So that's what we're going to do now, is some practice questions. So wherever you have space in your notes, if you can find some blank white space where you can do about 5 or 6 examples, or if you don't have that kind of white space, then maybe get a piece of paper. I have lined paper over there and scrap paper over there. You have a question for me? I'd rather you didn't write on the table just because I want you to have it in your notes, but if you want to and you have your own marker, go for it. It's completely up to you. I'm not going to collect this. This is just for you. Boop. So this says number 6. That means I took this right out of the textbook. Our job is to figure out what f over g equals, find its domain, figure out what g over f equals, and find its domain. And no, they're not the same. They're different. Now, I like to teach methods that always work every single time you go to use them. My suggestion every time is to find the domain before you simplify. Reason why. You remember yesterday, once we simplified one of those questions, our 2 radicals became a single line, but the line had a restricted domain. We did that by finding the domain before we simplified. So I give you a moment just to try it out on your own, just to see if you can. I mean, the division should be relatively easy, but can you get the domain correct on your own? That's what I want to know. So I'll give you a moment while I pause the video. So I have a brave volunteer. Let's see, f over g. F over g of x. This one should be pretty straightforward. What did you get for it? No, not the final answer. What did you get for your function? Yeah, the equation. You're still giving me your answer. No, I mean like this. Like, how did you get there? You did this. Like, that's the function. That is f over g. So well, the question says to actually find the function. So on the test, these look a lot like questions on my test. On the test, I want you to actually find the function and then find its domain. It would be like a multiple select question where you have to choose the correct function and the correct domain. So from there, walk me through. So you clearly have a domain. Can you walk me through how you got there? And you said you think the domain is x's.
I just did one f of x and I did.
Okay, so what did you do for finding the domain of f of x, which is the top of my fraction? How did you get there? Yeah? Right, so he said that the inside of the square root has to be greater than or equal to 0, because clearly you can't take the square root of a negative number. So for that, you have x minus 2 greater than or equal to 0. And you solve for x, and that's how you got that x was greater than or equal to 2. Great. What about the bottom? You did the same procedure? Okay, great. So you wrote x plus 4 is greater than or equal to 0? You sure? Uh-oh, a couple people are freaking out. Ash, what's the problem? There we go. It can't be equal to 0 on the bottom. So even though your final answer is correct, just getting there, we just want to make sure we have it right. But your final answer is right. Okay. But we know that it can't be equal to 0, so strictly greater than. Strictly greater than 0. And you said you did the same thing, so at this point you just subtracted 4. And you have x is greater than negative 4. Well, we have a unique situation here. We have overlapping domains. You said the answer is x is greater than or equal to 2. How did you choose that one? Because they overlap. What made you choose x is greater than or equal to 2? Well, my function seems to have two different possible domains, doesn't it? Why did you choose one of them over the other one? Because it looks nice. Here's the thing. I feel like you knew the right answer. Your gut told you it was the right answer, and maybe you weren't sure why. Always trust your gut. The answer is that x is greater than or equal to 2. But why? Let's say I've got a student sitting at home and doesn't quite know. Ethan, your hand went up first. Why choose that one? So you were saying the bottom domain says x has to be greater than -4, and you're saying, and the top one is already greater than -4. That is kind of it's right along the same ideas, but I'm looking for a more specific. How would you have known, Michael B?
Yeah, so while it's greater than or equal to 2,
Mhm.
satisfies both of the conditions, but if it's between 2 and -4, then it only satisfies one.
There it is. He says that x is greater than or equal to 2 satisfies both conditions, and any number that happens to land between 2 and -4 doesn't. So there's our problem. If let's say this bottom one down here, it allows me to use numbers like 0, but you can't plug 0 in right here. Basically, the rule comes down to this. Whichever domain is more restrictive, that is the domain you must listen to. Because listening to the less restrictive one might get you in trouble. Kind of like you go to mom and you go, Mom, can I stay out late tonight? And she goes, I don't know. Go ask your father. And your father says, oh man, you better go ask your mom again because I know that I'm too chill and my answer is probably going to get you in trouble. You got to go with the more restrictive answer. Whichever one allows less answers is going to be the answer, so to speak. That's what a weird way to say it. The more restrictive one. Michael B put it perfectly. Any number between 2 and -4 would have failed us miserably. And Thomas, you knew, your gut told you that it was 2, greater than or equal to 2. Well, I mean, I believe it. I really do feel that you just like, yeah, that had to be it. You didn't know why, but you knew. I mean, yeah, that happens. I mean, it happens. Let's see. So our final domain ends up being the more restrictive one, and I'm going to use interval notation because I prefer that because that's what's on my tests. Alrighty. Well, to do the other one, you just flip it over. G over F. Oops, I forgot my X. Oops, squeeze it in there. Gets us square root of x plus 4 over the square root of x minus 2. So we know that the domain of the radical itself isn't going to change much. The issue is now the x minus 2 has made it to the bottom. So when before in green we were allowed to include the 2, now we can't. And before in red we couldn't include the -4, now we can. So that's really the only thing that's changed. So on the top, and I'll use green again for the top, we have that x is greater than or equal to -4. And on the bottom, we have that x is greater than, strictly greater than, positive 2. So clearly the more restrictive one is x is greater than 2. It includes less numbers, so to speak. Yeah, they both include an infinite number of numbers, but there's a smaller infinity, if you want to think of it like that, in the bottom. So our domain this time is not including 2. And believe it or not, the graphs look completely different. It's pretty neat. Okay, not so much fun. How about compositions? I like compositions. Doink. I have given you an f of x and a g of x. I'm asking that you compose in both directions and find their individual domains. Using the idea of more restrictive or less restrictive might help you here, but it doesn't have to. But you never know. You never know. So once again, I'll pause the video, give you all some think time. That's more than enough think time. It's more than enough think time, and I can tell by the level of chitter and chatter in the room. Either they don't know how to do it or they know exactly how to do it, right? Or they're anxious to see me do it. One of the two. All right. One of the three? Two? One? I don't know. How many? F of g of x. Just like I did yesterday, I will switch the colors because I feel like that makes it easier to see. I'm going to make the blue one be f, so I have 1 over. Here is me plugging in g of x. And there, that's actually as simplified as that gets. You can't really clean that up any better. Could we rationalize the denominator? I mean, we could, but who cares? Okay. So I like this. This is a fraction. And the number one rule for fractions is that you cannot divide by 0. So the first thing you'd have to do is figure out what would have made... Ta-da! Okay. Okay. What would have made the denominator equal 0 because it's not allowed to happen, basically. So I'm going, hey, that denominator can't equal 0, and I'm going to solve for x. I add 1 to both sides. Like that. And then I square both sides. This does not create a plus or minus. It's a one-way street. Canceling a root with a square does not create a plus or minus. Canceling a square with a radical does, because the square could have been hiding negatives from you. So what this tells me is that, x cannot be the number 1. Okay, x can't be 1. The other thing we're dealing with here is we have a radical. And what's underneath the radical must be greater than or equal to 0. Can my radical be equal to 0 this time? Yes, it can, because the square root of 0 is 0, but 0 minus 1 is negative 1, and that's not a problem. The domain is actually both of these things. It begins at 0, goes up to 1, but stops right before it gets there, hops over it, picks up back at 1, just to the right of it, and goes forever to the right. So, just curious, hands up if we got that question right. So close? Yeah, I got a few people at home, anybody?
I missed the 0.
All right, I got a few people get it there. Yeah, you have a question for me? Yeah, what's up?
When you put bracket,
Yes.
that means it's not included and it can't be, or
No, the bracket means I can use it.
okay.
Think of it, it's a closed dot is what it is. Like on a number line, you're closing it. And the parenthesis means that was my boundary, but I didn't get to actually use that number. That's what it means. I could get darn close to it, though. Okay. Yes?
Why is it 0 instead of negative infinity?
Okay, so I can't include negative numbers. The reason why the question is why 0. I can't include negative numbers because I can't plug negative numbers into this radical. That's why. So what we did was the part of the domain came from the fact that the bottom of a fraction can't equal 0, which is what I did to the right. The other part of the domain was whatever's underneath a radical can't be negative. So that was what I did over here. And then I just said, well, this is everything to the right of 0, but this says, but don't include that number, so I can just hop over it. Okay. Yes, Thomas. Well, that's why I said the idea of more restrictive is a good idea. And I said it's usually the more restrictive domain. But that's only if we're talking about overlapping domains. These things technically don't, you wanted to say where they overlap? I cheated and said x can't be 1, right? What I should have said was negative infinity to 1 union 1 to infinity. And then I ask you, what's more restrictive? Well, this is more restrictive, correct? It's a lot less numbers, so to speak. However, the number 1 would have been part of this domain, and you know that 1's not allowed. So you combine the two ideas and go, well, I'll go with the more restrictive domain, but I'll hop over the one number that's going to cause me a problem for the other part. Yeah. Okay. Just overlapping. I'm going to go ahead and compose it in the other direction now. And if you would like to try to redo it and beat me there, you can. What's that? You hit a roadblock, huh? Yeah, let's see. G of f of x. Oh, I like this one here. I like this one. It gives me the square root of 1 over x minus 1. There. That is not the simplest form, but I told you I like methods that always work. Finding the domain before simplification will always work, but it's not always the easiest. So using what I taught you, I'm going to find the domain before I simplify. Do you have a question for me, Jarrell, or are you just stretching? Just stretching, okay. What do we know? Well, from right here, you know that x cannot be 1. Simple. Now you have a question? And there we go. So what he was also saying is inside the radical can't be negative. But you specifically said can't divide by a negative. Why'd you say that? Because the 1 is already positive. So the only way that that fraction could have been negative was if the bottom was negative, right? So Jarrell realized, okay, underneath the radical can't be negative, but the 1 is not an issue. The 1 that's on top is already positive, and the only way this fraction is negative is if x minus 1 is negative. So what we're going to say here is that x minus 1 cannot be negative. Can x minus 1 be 0, though? No, it cannot, because it's at the bottom of the fraction. So it has to be strictly greater than 0, which adding 1 gives you that x has to be strictly greater than 1. So x can't be 1, but my domain is x is strictly greater than 1. Oh, yeah. See, that's not actually a problem because this one right here already doesn't include 1. So the domain is just 1 to infinity. Yeah, 1 to infinity. 2 zeros next to each other because I can't draw infinity symbols. They always look like squashed 8s. I can't do it. I can't do it, so I just draw double O. Isn't that neat? What a fun question that is. Someone sarcastically said, so fun. I think it is fun. It gives you a chance to really think your way through the mathematics. And Jarrell, I'll be honest with you, in first period, nobody realized that. What one person did realize, though, remember I told you it's easier to find the domain. It's not always easier to find the domain before simplification, but it will always work. What we could have done, and let me just start. The answer is not going to change, but I'm just going to erase this. Just going to erase this real quick. It won't change the answer. When you take the square root of a fraction, you know that's the square root of the top and the square root of the bottom. So I feel like this is what Jarrell did in his head. The square root of 1 is 1. And on the bottom, you're going to have this. You see, if you simplify it to there, this one's actually much easier to do. But it's not, it doesn't all, it will, you saw it fail yesterday a couple times. Simplifying first can create problems for you. Finding the domain first will never fail. It's just not always the easiest way. So, I don't know. So what do? The answer is whatever you're most comfortable with. I mean, I just make it a habit of doing it before I simplify, and then later on, if it was easier, I go, okay, well, I mean, that's one of those times where I worked a little too hard, but whatever. Yeah. You didn't do that. No, I'm saying I felt like you didn't realize it, but that's the logic you were doing in your head.
I just did 0 minus 1 gave you a negative.
Right.
And then you took 1 divided by a negative, and you get a negative on the radical.
Yeah.
And there could be another negative, and you get a negative under the.
It's, believe it or not, it is the exact same logic, though. Because if you think about it now, let's say we simplified right there. And we said, okay, let's find the domain of this thing. Well, inside the radical can't be negative. And since it's the bottom of a fraction, it can't be 0. Answer's done. You see, it's the same amount of, logic, just done in slightly different order than what you did it. But your thinking was perfect. It was very good. Very good. And we have some time still to pull off these bad boys. So we have a couple relations that are non-functions, and we are going to define them implicitly by isolating y. So go ahead and get y by itself and define the functions implicitly. I can tell you the first one's a sideways parabola. And in the essence of time, I'll get moving on number 38, obviously stolen from your textbook. Trying to get y by itself. First thing you should do, subtract x. And if you wrote negative x plus 25, it's the same thing. And at this point, you would have to take the square root of both sides. So for this one, getting y by itself, shoot, relatively easy, right? You just have to remember the plus or the minus. So that is two different functions. The positive square root of 25 minus x and the negative square root of 25 minus x. You can't simplify the 25 for the same reason why I couldn't simplify the 4 minus x squared earlier. The plus and minus, the plus or minus, excuse me, that's between the terms stops you from doing that. No, you just can't simplify it. If it said 25x squared, or if it said 25x, could you simplify some things? Yes, but that's multiplication. This has subtraction in between it. You can't do that. It's like this. If I gave you, let's just say I gave you this. I'm going to erase in just a second. Is this x squared plus 4? No, it's x squared plus 4x plus 4. You'd FOIL, right? You can't apply that second exponent to the x and the 2. Well, every radical is an exponent. It's the 1/2 power. So it's the same idea. You can't apply it to those two things because they're separated by plus or minus. Wow, that didn't work at all. Catch up with me, board. So the real question is, were you able to pull off number 42? Let's find out. Let me subtract x from both sides. And this time I'm going to write it as negative x plus 1, but for a reason. I'm going to divide both sides by that negative 1. Gets me there. So what does absolute values do to numbers? Makes them positive. So just like squares, it hides negatives from you, doesn't it? So what that means is it could have been y equals x minus 1 or negative y equals x minus 1, and you never would have known. Because if you take the absolute value of y or negative y, you get y. So the second equation, to get y by itself, you just divide everything by negative 1. And you have implicitly defined your function with this and this. And what is neat about those two straight lines? These are perpendicular lines. How neat. That is everything for today. Yes, Bryce.
So if we just see something that says define implicitly, can we just solve for y?
Define the relation implicitly means get y by itself.